Welcome to the 10th lecture from chapter number 7. We are studying VLSI design. In previous lectures, we have been studying about the DC and transient analysis of CMOS NOT. And in this lecture, we'll study about the power dissipation of a CMOS NOT gate. CMOS NOT gate can be implemented using one PMOS MP and one NMOS MN. Like this, we have been studying in our previous lectures. We have also been studying about the VTC in one or two of our previous lectures. VTC stands for voltage transfer characteristics. It is the result of applying DC analysis on CMOS NOT. And this is a graph plotted between V in versus V out. And we know that when we apply 0 or very small voltages at the input, MP is on because we know that this is source, this is gate, and VSG is smaller than VTP. Sorry, it's greater than VTP, and this is on. And when we have very large voltages at the input, we have VGS greater than or equal to VTN, and this NMOS is on. So when MP is on, when the V out, when V in is very small, MN is off. MN is off. At this time, MN is off, and here MN is on, but MP is off. In the middle, we have studied that in the middle we have this condition coming true for both PMOS and NMOS transistors, and they both are on. And we also studied about this voltage. This is VM, the middle voltage, where Vin is equal to V out, and not only at VM but for voltages around VM, both MP and MN are on. Right. So if we draw a plot between Vin and ID, we see that versus Vin, if we plot ID, we have very small ID flowing through this gate when the input is either logic 0 or logic 1. Because when the input is logic 0, MP is on and we have VDD available at the output, but MN is off. This means very small leakage current is flowing through this gate from VDD down to ground. And when we have V in very large voltage, this MN is on but MP is off, and again we have very small leakage current flowing through this path from VDD to ground. So there is a very small voltage, very small current flowing through MP and MN when the output is at logic 0 or at logic 1. But what's about the voltages that are in between V0 and VDD? For example, VM. For example, the voltage VM, the middle voltage. For the voltages equal to VM and around VM, we have both transistors on. In this region, we have both transistors are on, and the current that flows through this path from VDD to ground is maximum when we are at VM, because the resistance offered by these two transistors is equal. Right. So power can be thought of as the DC power that is dissipated in this gate when we are at some output voltage, and dynamic power that is dissipated in this circuit when we are transitioning from logic 0 to logic 1 or vice versa. So there are two different types of power that are there in a CMOS circuit. Right. The output is either at logic 0 and logic 1. The power that is dissipated is PDC, and PDC is very small because it is VDD times this small current IDQ. Just why is this small? Because IDQ is small. This quantity is small. Therefore, this PDC is small. P dynamic is a significant power that is dissipated in this circuit when we have a current flowing, the max current flowing or around this area, in this area. Right. We have in this area when we are at voltages around VM, we have maximum power dissipated in the circuit because there is maximum current I. If we call this current I, it can also be thought of as Q over T, because current is thought of as the charges, rate of flow of charges, Q over T, where T is the time period of the wave that we have applied as input to this gate. And Q can be written as C times V, the output capacitance is C out. We studied that there are many capacitances Cn, Cp, Cn and Cout, and cumulatively we call that Cout. We studied in our previous lecture that Cout is the sum of three capacitances: the outward capacitance of PMOS, of NMOS, and the load capacitance, times VDD times F. Right, VDD, this V is VDD because the max possible voltage is VDD, and 1 over T is the frequency. So dynamic power is Cout times VDD squared times F. This is a very interesting expression for P dynamic. This means that if you want to reduce, we know that power dissipation should be as small as possible. So if we want to reduce this dynamic power, we have to work with smaller frequencies, but we cannot because the modern day requirement forces us to have speedy circuits. Modern day requirement is to have speedy circuit, So we cannot have this implemented. We cannot reduce dynamic power by reducing frequency. However, we can reduce dynamic power by reducing the power supply voltage VDD, and it is proportional to the square of the term. That makes it more significant because it is proportional to the square of the VDD. So this is interesting, as well as it is a very significant term. So the modern trend is to reduce VDD, and we see in our in the lectures to come, we'll see that we'll be working with circuits that have VDD smaller than 5 volts, maybe 3 volts, 3.5 volts, or even 1.8 volts. Right, that's all for this lecture. In the next lecture, we will continue with more complex CMOS circuits. Thank you.